welcome to the third part of this module. Let's start with the applications of GIS in precision agriculture. The key areas of application of GIS in precision agriculture include the following. 1. Soil mapping and analysis. Soil is a critical factor in agriculture, and its properties can vary significantly even within the same field. Amidst the growing food demands of an increasing population, agricultural intensification frequently depends on excessive chemical and fertilizer applications. While this approach initially boosts crop yields, it affects long-term sustainability through soil degradation and compromised food quality. Thus, prioritizing soil health while enhancing crop production is essential for sustainable food production. Understanding the physical and chemical properties of soil is essential for determining the needs of precision agricultural management. Among the key physical factors influencing plant growth are soil texture and moisture. Additionally, soil texture plays a crucial role in regulating nutrient availability and water retention capacity. GIS allows farmers to identify areas of soil degradation and implement targeted soil management practices. GIS enables farmers to create soil maps by collecting data from field samples or sensors that measure soil characteristics such as texture, sand, silt, clay, organic matter content, pH, electrical conductivity, and nutrient levels, e.g., nitrogen, phosphorus, potassium. These maps help visualize spatial variability in soil properties, allowing farmers to apply fertilizers and soil amendments, e.g., lime, organic matter, etc., at variable rates that match the needs of specific areas in the field, thereby reducing fertilizer waste, runoff, and the risk of water pollution. Second, crop health monitoring. Using remote sensing technologies, e.g., satellites, unmanned aerial vehicles, or drones, GIS can capture high-resolution imagery of crop fields to monitor plant health and to obtain the following data. Vegetation indices, NDVI, is commonly used to assess crop nutritional status, indicating soil cover and chlorophyll content, ergo crop vigor, and, consequently, productivity. It measures plant health by analyzing how vegetation reflects near-infrared, which healthy plants reflect more, and visible red light. NDVI is that difference expressed as a number ranging from -1 to 1. High NDVI values indicate healthy, photosynthetically active plants, while lower values suggest stress caused by factors such as drought, pests, disease, or nutrient deficiencies. Thermal imaging. GIS can incorporate thermal data to identify hot and cold spots within a field, e.g., stressed plants experiencing drought or nutrient shortages often show temperature changes that thermal cameras on drones or satellites can detect. This helps pinpoint areas that need immediate attention. Farmers can leverage these insights to proactively address these issues by applying water, nutrients, or pest control more effectively and efficiently. Third, precision irrigation management. Water is a critical resource, and precision irrigation techniques help maximize its use. By integrating data from soil moisture sensors, weather stations, and remote sensing, GIS can map moisture variations across a field. This spatial data enables farmers to create accurate irrigation schedules tailored to the unique moisture needs of different field zones. GIS supports variable rate irrigation, VRI, allowing irrigation systems to apply water at varying rates across the field based on soil moisture or crop needs. This helps avoid overwatering, which can lead to nutrient leaching, or underwatering, which can cause drought stress. Additionally, farmers can utilize evapotranspiration ET models, combining GIS with climate data to estimate water loss through evaporation and transpiration. This information aids in scheduling irrigation more effectively. This ensures efficient water use, prevents water stress, and promotes uniform crop growth while reducing energy and water costs. Fourth, yield mapping. Yield maps are generated using sensors mounted on harvester that track crop yields as it moves across the field. Yield mapping enables mapping spatial yield variation. Yield monitor data, combined with GPS data, provides precise information on where higher or lower yields occurred across the field. Overlaying yield maps with other data. By combining yield maps with additional information such as soil data, topography, or management practices, farmers can identify patterns and correlations between yield and factors like soil fertility, pest pressure, or water distribution. This process helps optimize future inputs like fertilizers or seeds and improves decision-making for planting strategies, crop rotations, and overall field management. Fifth, pest and disease management. Pests and diseases can spread quickly, making early detection crucial for effective outbreak management. GIS plays a vital role by analyzing pest and disease distribution, tracking pest movement, mapping hotspots, and examining how environmental factors like temperature, humidity, and wind influence the spread of pests and pathogens. Predicting outbreaks. Using overlays of pest, climatic, and field data to forecast disease or pest outbreaks. This enables the implementation of precise pest control strategies such as pesticides, biological agents, or traps only where and when necessary, minimizing costs and environmental impact. Detecting early signs of crop stress. Utilizing remote sensing to monitor changes in vegetation reflectance helps to identify early signs of pest or disease stress before visible symptoms appear. Sixth, climate and weather data integration. Climate variability can significantly influence crop production. GIS empowers farmers to merge weather and climate data with field information to forecast extreme weather events, predict potential threats like frost, drought, or heavy rainfall. By combining weather forecasts with topographical data, such as identifying low-lying areas where cold air accumulates, farmers can take preventive actions like irrigation or crop covering. Monitor microclimates. Analyze temperature, humidity, and wind variations within large fields caused by landscape features like hills, trees, or water bodies. This localized understanding helps farmers implement more precise, climate-adapted crop management practices. Correlate climate patterns with crop yield. Integrate historical climate data with past crop performance to assess the impact of weather variability. This insight supports more informed, strategic decisions for future growing seasons. Variable Rate Technology, VRT. VRT is an essential component of PA and is becoming increasingly popular among large landholders. VRT encompasses a range of technologies rather than referring to one. In VRT, the collection of field variable data and other input information is crucial for determining the appropriate quantities of chemical inputs needed for specific fields. To address systemic challenges in agriculture such as environmental degradation, climate change, food security, and farmer well-being, improving nitrogen use efficiency is essential. VRT offers a solution by applying fertilizers precisely, delivering the right amount at the right time and place to match crop needs. This approach minimizes nitrogen losses, i.e., it reduces fertilizer usage without compromising yields, and supports the development of a more sustainable agricultural system. The adoption of VRT introduces an automated solution to address the variability in agricultural fields, where factors such as soil texture, water content, organic matter, nutrients, and many others create a highly variable environment. This variability, combined with plants' biological flexibility, leads to differing crop responses. The practical implementation of VRT, according to Patil and Shanwad, 2009, is a cyclical process that includes the following steps. Data collection, interpretation of the collected data, implementation of appropriate management responses, and monitoring the results in a continuous learning process. The effectiveness of data collection relies heavily on the resolution and accuracy provided by the sensing technologies. Data can be gathered through various methods, such as soil sampling, satellite imagery, drone photography, yield mapping, or handheld devices. Soil sampling may be done as raster sampling or based on partial areas, such as those generated from yield maps. Grid sampling, for instance, only provides adequate nutrient distribution data for smaller grids of 0.25 to 0.5 hectares. There are two primary site-specific management methods for nitrogen application: map-based and sensor-based approaches. The map-based approach focuses on creating management zones, which involves collecting geo-referenced data on yield, soil properties, or crop biomass indices. The data is analyzed to generate a site-specific map of properties, which can then be used for variable rate applications. Spatial data on soil and plant properties can be obtained from aerial or satellite imagery or soil samples. GPS or more accurate systems like Differential Global Positioning Systems, DGPS, are used to determine the location in the field during sampling and application. On the other hand, the sensor-based approach employs real-time sensors mounted on tractors with feedback control systems to measure soil or crop characteristics. This real-time data is immediately available for variable rate application. Although sensor-based technologies can function independently of GPS and GIS in the field, they are often integrated with these systems to track input records and monitor annual variations in input use. Three types of sensor-based nitrogen application methods exist: online, offline, and an online method combined with map overlays. The online method, which is common for sensor-based nitrogen fertilization, converts spectral indices measured by sensors into nitrogen target values and application technology. This method is particularly useful when plant development is insufficiently advanced to be detected by sensors at the time of application. Despite differences in these two approaches, their effectiveness largely depends on the accuracy of the environmental data collected during the data gathering phase. 5 different methods for collecting the necessary information based on the various technologies have been identified. These are 1. Soil sampling. 2. Real-time sensing with tractor-mounted crop sensors. 3rd, handheld devices. 4th, satellite-based sensing. 5th, drone-based sensing. All collected information must be processed through a management information system, which involves investment and quasi-fixed costs. These different sensing methods are often used in combination. For instance, real-time information from tractor-mounted crop sensors can be integrated with soil sample data and field history records to continuously adjust nitrogen rates in the field. Moving from the first to the fifth method increases the quality of information available on plant nutrient needs. We have come to the end of the third part of this module. Stay tuned and let's explore the last part together.